Thank you for your presentation again. So I'm Soufiane Krik from the Free University of Bolzano in Italy, and today I'm presenting our work on the agave plant, so exploring the agave plant, especially the fibers extracted from this plant for sustainable and flexible electronics. So to begin, I would like to recall some numbers reported by the World Health Organization in October 2024. So far, we have an annual e-waste of 2.6 million tons, which is resulting in a global in 2022 of 62 million tons, from which only 22.3% are collected and recycled. It is expected that we will reach 82 million tons by 2030. So researchers have been developing new strategies to overcome these challenges in reducing e-waste, minimizing environmental impact for a sustainable future. And among these strategies, we have the use of biodegradable, biocompatible, and bioresorbable electronics and substrates in order to enhance the waste management, minimizing the environmental degradation for a sustainable future. Literature reports the use of natural materials such as animal-based substrates, including buffalo horn or mother of pearl, chitosan-based substrate, silk fibrium-based substrate. And another source for natural materials is the plant fibers-based substrates such as the cherry, cacao, coffee, and coconut. Agave silk fibers are known for the high mechanical strength, durability, and natural degradability. They are sustainable and biodegradable, and their process is eco-friendly. There are many types of agave plants, including but not limited to Siciliana, Tequilana, and the Sabra. Sabra is a name that Moroccan people gave to the type of agave that is in Morocco, especially in the north part of Morocco, the city of Fez. So the Tequilana one is known, as you know, for the tequila, so for the production of liqueurs. While the Sabra in Morocco, they are using it for the production of rugs, twine, artisan crafts, rugs, and mugs. But so far, we couldn't find any literature reporting the use of these fibers for electronics. So during a trip to Morocco with some friends, since I'm from Morocco, so I brought some friends to Morocco for a trip, and we said, why not exploring these fibers for electronics? Indeed, so from a local forest in Morocco, we got the leaves of the agave, and if you see, as soon as you break the leaves, the fibers are really clear here. So to process these leaves, we first removed the apical and lateral spines, and we divided the leaves into several segments. So we dried the segments, and then we put them again in water for 2 weeks in order to facilitate the extraction of the fiber. After that, we manually beat the leaf, the segments, and then we dried them and we extracted the fibers. So the next step, we should process these fibers into a powder, and then dissolve it in order to deposit. So for this, we mechanically process this fibers, and then we get dispersed it in deionized water. So we tried several solvents, but so far deionized water was the best. And then we steer it at room temperature for 24 hours. And then we drop cast it on Teflon plates. So also here we tried several surfaces, but it was like really hard to peel substrate. But so far Teflon plates showed good results. We dry it for the evaporation of the solvent. Then the results is this kind of substrate, which we are like 5 centimeters length. Then we start with some characterization of this substrate. And as you can see here, confocal images show a successful deposition of the fibers with a length ranging from 224 to 237 microns and a width ranging from 20 to 37 microns. the measured average thickness was around 83 microns, while the roughness was 2.6, about 2.6 micrometers. Then, okay, I changed that slide after the talk of Professor Irimia Plado. I put preliminary here, so because it's preliminary. So yeah, biodegradability test, we used this custom-made setup in which we monitored also the pH and the conductivity of the solution. So we need to improve this setup, let's say, in order to say, okay, we did the biodegradability test of our substrate. Anyway, the results showed an onset of the solution of the substrate in approximately 20 hours. So it started to dissolve, and it was almost dissolved, complete dissolution after about 2 days and 7 hours. So the monitored pH and the conductivity of the solution was constant, so it was stable more or less, which means that the substrate is not polluting. Then, as a proof of concept, like very first test that we have done, it's just we say, okay, can we print on the substrate or not? So we made a U shape and we screen printed the silver paste on this substrate, and then we used like printing paper as a reference. Then we measured, like, from time to time we measured the resistance, and as you can see here, it was like stable even after 7 months. I should note that 2 samples were stored in just like not controlled environment. It was like in a petri dish in a cardboard, so the results are promising. Then we want to try if our substrate is compatible with high vacuum deposition tools. So we printed a temperature sensor, an RTD. We spattered the cardboard on top of our substrate, and the confocal image can show that we have a uniform deposition of the cardboard, and the pumping time to reach 10 to minus 6 millibar was about 15 minutes, which prove the compatibility of our substrate with high vacuum deposition tool. Then we characterized our temperature sensor. The characterization was done more or less the same as my colleague that presented before. So we have done the characterization from 25 to 55 degrees Celsius, heating and cooling steps in a 5 degree steps. The sensitivity of the sensor was 0.26% Celsius minus 1 during the heating phase, while during the cooling phase it was 0.24% Celsius minus 1. Then we have done a repeatability test, so doing 10 cycles measurements going from 25 to 55, and we can see that the resistance has a small drift, which was like about 3%. But I mean, we can assign this drift more or less to the roughness of the sample because it was like not so smooth. So then, in order to assess the mechanical properties, we placed our device on a curved surface with different reading, and then we measured the EV curve of the sample. As you can see, the resistance didn't change a lot, so we can say that our substrate can withstand deformation and strain. So as conclusion, I can say that we successfully extracted, dispersed, and deposited agave seed fibers. We got good, but not the best properties of the substrate, let's say. We are improving. And as proof of concept, we fabricated and characterized a temperature sensor. As outlook, we are now working on optimizing the roughness and transparency of the substrate, and we are getting to the point, let's say. Then we would like to do the real biodegradability test, biocompatibility and bioresorbability. And yes, we would like to use this substrate for other applications such as OLED or PVCs. So that's why we are like concentrating on also the transparency. Yeah, we are happy and open for collaboration. In order, if you have any potential applications, we can provide order of fibers. We may also conductive fibers with a length ranging from 50 to 70 using P.PSS, carbon-based paste. We can provide powder or the solution itself, or we can provide the final substrate, the final, let's say, optimized substrate. Last but not least, I would like to acknowledge PMDI and the RISE-UP projects that are funding this project. I would like to thank you all for following my presentation and the Prime Research Group member teams, especially my supervisor, Cacialli. Thank you.